All right, let's try to do a little bit more than we did yesterday. Again, like I said, I don't think there's any way we're going to finish this lesson because it's crazy long. But we'll get a big chunk of it done. So this part is called classifying numbers. Okay, we're going to give names to certain groups, certain sets of numbers. Girls, here we go. Classifying, oops, forgot. What's that? Oh, why is that still up there? Let's do that. Come on. Oh, goodness. Okay, maybe that'll do it. There we go. That'll work. All right. What did I say we're going to do? Oh, I got to change this. Man, I thought I had everything ready. One day, I'll have all this ready before I start recording. Maybe. Middle of the year. All right, classifying numbers. Write that down. Classifying numbers. All right, the first type of number is called a counting number. Counting. Because when we start counting stuff, if I started counting the people in here, what number would I start with if I started counting everybody in here? 1, right? I'd go 1, 2, 3, 4, 5, right? I wouldn't go negative. I wouldn't go 0. Okay, counting number is counting or, that's a slash. Sometimes we call it a natural number, right? Counting numbers or natural numbers, it's the same exact thing. And we'll use an N for natural. That's what they usually use for these. And then I'll put this in a little brace. We did those yesterday, didn't we? And again, what number do I start with counting or natural numbers? 1. So it's just 1, 2, 3, 4, and then it just keeps on going, right? I'm not going to sit here and write 5, 6, 7, 8, 9, 10 until it goes to infinity because I'll never get there anyway. So what do I show? What do I put in here? Put it dot, dot, dot. That means it just keeps on going forever. It follows that pattern and it just keeps on going forever and ever, all the way to where? I said it already? Infinity, right? And where else? Beyond, right? All right. What about this? Whole numbers. I think they use a W for whole numbers. Now, it's very, very similar to the natural or counting numbers, but if I do a whole number, when I think of a hole, I think it's empty. There's nothing in it, right? If I dig a hole, right? I mean, there's like dirt at the bottom of it, but like in the place, I took all the dirt out, what's left in there? Nothing, 0, right? So what does a whole number start with? 0. And then it's just like the counting numbers. All right, but it just starts with a 0. So a whole number, the only thing difference between whole numbers and counting numbers is whole numbers have a 0 in it and counting numbers do not. So that's pretty easy. You've been doing this stuff since middle school, haven't you? Doesn't it seem like every year they start off teaching whole numbers and all that kind of thing? All right, here's one that you're going to use a lot. And it's a word that students forget. I don't know why, because I say it all the time, and then halfway through the year, I say something about this word, and they're like, what's that? I'm like, we've been talking about it all year long. So here it is, second day of teaching. I'm going to show it to you, and I do expect you to know what these are. They're called integers. Anybody heard of integers? Yeah, of course you have. In Algebra 1, you heard integers. Algebra 2, you guys have Algebra 2 last year? Yeah, you probably heard of integers, didn't you? Yeah. Trying to think of I just taught it yesterday in my Algebra 2 class. Let me see. Let me check my notes from Algebra 2. And I forget the letters already that we used. Hold on. Give me a second. Let's see. Algebra 2. Hold on. Give me a second. Integer. Yeah, we use a Z. That's what I thought. I wasn't 100%. I've seen it, people use an I, but they use a Z. All right? Capital Z, But a lot of times they make it look kind of crazy. They put this little extra bar in there so it looks a little wacky. You don't have to do that. Just make it a Z, right? It's supposed to be kind of parallel to this diagonal bar. Now I really screwed it up. Anyway, you kind of get the idea. But a lot of times they'll do that, put that weird thing in there. So what are integers? Integers are kind of like whole numbers plus all the negative whole numbers. Technically, you can't say that because if it's a whole number, it's not negative, right? But in our mind, we're thinking, oh, negative numbers, whole numbers. It's okay to think of it that way. So it's kind of like all the whole numbers. So you do have a 0, a +1, +2, +3, and it keeps on going. But you also have negative numbers as well. All right, so what's the next negative integer to the left of 0? -1, then what else? -2, -3. I didn't make this big enough, so let's scooch that over. That's the beauty of my little machine here. And then we'll put a ... because it keeps going to the left as far as it can go, and it keeps going to the right as far as it can go. All right? What about the number like 1.5? Is 1.5 an integer? No. What about -3/4? No. All right? Because none of the in-between numbers are counted as integers. It's just these numbers, okay? It's just the ones that kind of come out even, I guess. Not even as in odd even, but they don't come out with a little point anything. It's always 0.0, all right? The integers always have a 0.0. So those are your integers. And close that off right there. Everybody got that? So they're kind of like whole numbers plus the negative whole numbers, if you want to think of it that way. Some math teachers would have a fit if they heard me say that, but that's okay. They can have a fit. All right, let's talk about this kind of number. Let's talk about a rational number. What in the world is a rational number? There's a lot of rational numbers. What word is inside rational number? It's a ratio. What is a ratio? What's that? That's a rational. R-A-T, what? This? Yeah, remember I said it's a Z with that weird bar? All right, it just looks a little different. You can just make it a Z. But what word is in rational? Ratio. What's a ratio? Ratio is like a comparison between one thing and another. In math, what is a comparison between one thing and another? It's basically a fraction. All right, so really any number that you can write as a fraction is a rational number. So like 3/4. What kind of a number is 3/4? It's a rational number, isn't it? Now, is it a counting number, whole number, integer? No, but it is considered to be a rational number. Any number that you can make. What about 7? Is that a rational number? It is, because you could always make this what? 7/1, okay? Or you could make it 14/2. That's 7, isn't it? So 7 could also be considered a rational number. So any of these numbers could still be considered a rational number, all right? So rational numbers up here, all those other ones are underneath rational number. We okay with that? Anytime you can make it a fraction. What about 0.25? Is that a rational number? It is. Why? Okay. What would that fraction be? Very good. I picked an easy one, all right? So that would be 1/4. All right, so that's a fraction. Everybody good with that? What about what's that? A symbol R, and they give it a weird R. They put like 2 bars like that. Actually, no, they only, I'd have to look. I don't really care what the symbol is, to tell you the truth. I think this is for real numbers. The R with the 2 bars right there is for a real number. The rational number, I think they might use the letter I for, but I don't know. I don't really care, to tell you the truth, what it is. We just want to know what rational numbers are. Because every once in a while, they'll have a problem. They'll say, blah, 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 the rational numbers, blah, blah, blah. And you're like, well, what's a rational number? Oh, yeah, it's any number that you can write as a fraction. That's a rational number. Does that make sense? That's all I care about that you know. What about this number? 0.3, 3, 3, 3. And I could keep doing this all day long. It'd be a pretty boring day, but I could never stop. So what's a better way to write that? 0.3 what? Repeating. Right, put a little bar over top of that. It means it repeats. Is that a fraction? Is that a rational number? 0.3 repeating. Are you stumped? Yes, it is. Why is it? What is the fraction for this? You don't know? What is it? Say it. 1/3. Exactly. It's 1/3. You can put that in your calculator. Put in 1/3 in your calculator. Put 1 divided by 3, and you're going to get 0.33333, and it's going to go to the end of the calculator. All right, that's 1/3. Now, tell me something about these two fractions. This fraction right here stops at that number, doesn't it? This fraction right here does what? It keeps going. It repeats, right? It repeats the same thing over and over again. So in order to make it a rational number, it either the decimal has to either stop or it has to repeat the same thing over and over and over again. Everybody good with that? All right. You can put any fraction in your calculator. Well, I don't know. Sometimes it may take more digits than the calculator actually has to start seeing where it repeats. But anytime you write a fraction, and you put it in as a decimal, you probably will see a pattern start repeating. What happens if you have a decimal and that decimal never repeats, or it doesn't stop, okay, and it never repeats? Well, that's called something else. That's called an irrational number. Just put an IR in front of it. That means it's not. The IR it negates it. It makes it not rational. So an irrational number, these are kind of strange numbers, but there's numbers you've seen before. For instance, like if I had the square root of 5, it's 2 point something. I don't know exactly what it is. Let me put that into my calculator. So what did I say? Square root of 5? Square root of 5. 2.23. I'll write it out as many places as my calculator has. It's 2.236067977. Now it kind of looks like it might repeat those sevens, but if I had a calculator that went out further than this does, you'd find out that it might repeat a couple numbers, but it doesn't repeat the same pattern over and over and over again. All right? So this is considered to be an irrational number. The decimal doesn't stop and it never repeats. All right? So square root of 5 is not rational. It's what? It's irrational. You got it? Here's another number that we used. A lot of you guys had me for geometry. Here's something that you use quite a bit. And you probably used this before you had me in geometry. And that would be this. What's that? That's pi. Okay? And pi is, most of you remember 2 decimal places, don't you? 3.14. But a lot of times, especially like elementary, later elementary, early middle school teachers, usually just say it's 3.14 and that's all you have to know. And a lot of times they don't even tell you like where it comes from and that kind of stuff. I did when I taught you in geometry. We talked about the circumference of the circle compared to the diameter of the circle. Circumference of the circle is pi times what the diameter is, and all that kind of stuff. So we talked about that. But it's 3.14159, and I thought I would remember a few more. Let me just put it into my calculators. 2654. Right. I should remember that just to, but it really doesn't matter, because to tell you the truth, nothing an average person has can measure anything that accurately anyway. If you had a tape measure, if you had anything, nothing measures it that accurately. There might be some really expensive scientific equipment that's in these crazy expensive labs that could measure something that accurately, but there's really no reason to learn pi over 2 or 3 decimal places, because nothing that we use can accurately measure it anyway. All right. These are squiggle equal signs. That doesn't look that squiggly. I'll try to make it a little bit better. What does that mean? A squiggle equal sign like that. It's not congruent. It's about what? Like, say, what would you say? Is it similar, or would you say? Approximately, right. Exactly right. That's the word, right? So you've got to bring somebody from Spain in to have you guys understand this. So it means approximately equal to. That's why I put a squiggle equal sign here. This doesn't exactly equal this, because what happens? This keeps on going, but it never repeats it. It never repeats the pattern. Same with this. Years ago, I used to have a little poster about that high, and it wrapped about 3/4 way around the room, and it was out to, I forget how many, I don't know if it was 100, I doubt it was 100, but it was out to like 80-some decimal places. And it was kind of cool looking because you saw all these random numbers going across the room. But at the very end of that poster, it said ... because it never ends. It doesn't stop at 100 places. It doesn't stop there. You could probably put it in chat GPT if you wanted to. Tell me what pi is. Here, I'll do it. I don't have it on my computer. I got it here on my phone. So let's see. What is the value of pi up to 100 decimal places? And there we go. There it goes. It's still going. Well, oh my. That's so funny. It's like super tiny. They made it tiny. They didn't even go like to the next line. That's weird. There it is right there. Here, somebody look at that. Here, take that. Quick. I can't reach because I'm stuck to my microphone. You see the pi? Yeah. That didn't look very exciting. Man, I think that's kind of cool. Look, it goes all the way to there, but it's really, really tiny, and it goes to 100 decimal places. You want me to read them all off to you? Here we go. I'm not just kidding. I'm not going to read off 100 decimal places. Anyway, but you could if you wanted to. I had a kid, I don't know, my 3rd or 4th year teaching, really smart kid, super lazy kid, never did his homework, crazy smart in math, crazy smart. He was like taking Calc 2 when he was a junior in high school. He was going to the University of Delaware to take calculus. And he claimed that he knew pi up to 100 decimal places. I'm like, okay, say it for us, right? He's like 3.14159, blah, 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 and he kept on going. And of course, I had nothing to check to see if he was right, but he said he went to 100 decimal places. Who knows if they were right or not? Nowadays, you can actually check to see. But there's really no really practical value in that. It's just a little party trick, right, that you could use, I guess. But now you can put it in your phone and you can look it up and you can check to make sure that they did it right. So anyway, why did we talk about pi that long? I have no idea. It's kind of interesting. Let me see what else I want to say about that. Okay, I already did that. Okay, let's talk about this. Remember I wrote that down? We didn't talk about what a real number is, but let's talk about that. That's the whole lesson. That's the name of this whole entire lesson. This gigantic, long marathon lesson. What is a real number? Basically, a real number is any number that you could think of. Any single number that's on the number line. It does not matter. If it's on the number line, then it's a real number. Well, if it's on the real number line, I guess I should say. So if it's on this number line, it's a real number. So like 0.723, is that a real number? Absolutely. That's somewhere on the number line. Okay, any number you could think of. You're thinking, well, Mr. Hamrick, what numbers aren't on the number line? Good question. I'm glad you asked. Anybody know? There's another set of numbers. Everything we've dealt with, I don't know, maybe in Algebra 2 you might have dealt with this stuff. Maybe not. They're called imaginary numbers. Have you dealt with imaginary numbers? Have you talked about them? That's right. There are things called imaginary numbers. We will get into that this year. I asked somebody in one of my other classes yesterday, I said, okay, there's real numbers, and there's also another kind of numbers that aren't real numbers. What are they? And they said fake numbers. And I hear that all the time. And there's, I didn't laugh. I mean, that's kind of makes sense. You got real, you got fake, These aren't fake numbers. They're numbers that exist, but they don't exist on the real number line. All right, it's really strange. I'll give you a sneak preview. Everybody ready? I know you're excited about this, okay? Alberto, do you know imaginary numbers? So give me an example of an imaginary number. Well, it's not that. So this would mean an empty set, or it doesn't exist. Imaginary numbers actually do exist. For instance, what if I said, what is the square root of 4 equal to? Say it. It's not a trick question. It's 2, right? Just plain old 2, all right? Everybody good with that? So what do we do? What do we ask ourselves? What number times what? Itself is equal to 2. I'm sorry, is equal to 4, right? Square root of 4. So 2 times 2, correct? Let's do another one. What's the square root of 16? What number times itself is 16? 4, okay? 8 times 8 is not 16. What number times itself is 16? What about this? What number is this? What's the square root of negative 25? Is it negative 5? Okay, hang on. You're right. I just want to save it for a second here. Is it negative 5? No, because negative 5 times negative 5 is what? Is positive 25. Are there any two of the same exact numbers that multiply to be negative 25? There's not, are there? Okay? So this is not a real number, but this is actually an imaginary number. Today's lesson is not really about imaginary numbers. I just like talking about them. So we'll eventually get into this later on, but I just want to show you this. So what we do is we define the square root of negative 1, which doesn't exist. Is there something times itself that's equal to negative 1? No, because look, anytime you multiply something by itself, it's either a positive times a positive, which is what? Positive, or it's a negative times a negative, which is also a what? Positive. Is there anything times itself that's going to give you a negative? No, so it doesn't exist. So what they came up with, I don't know who came up with it, but they came up with this idea that what we're going to do is we're going to define the square root of negative 1 to equal the letter I. I for, what do you think? Imaginary. Very good. Okay? So that's what they've done. And so if you take a look at this, watch what we're going to do. We're going to go 25 times negative 1. Do you agree? 25 times negative 1 is negative 25. So this is what we do. We take the square root of 25 and we multiply it by the square root of what? Negative 1. So now, what is the square root of just regular 25? It's 5. And what do we define the square root of negative 1 to be? What's that? Yeah, I did that right, didn't I? Did I say something wrong? Okay. So anyway, the square root of 25 is 5. And then what's the square root of negative 1? What do we define it to be? It's just I. Okay? And that is what your answer is to that. We'll get into it later. It wasn't even in my notes to do that, okay? It's just kind of fun to do. I think it is. Maybe you don't think it's that fun. All right? We good with that? All right. Let's talk about something else. And I always wonder, because I've never really learned like the practical application of I, even though I took a class. We call these complex numbers. These imaginary numbers are part of a bigger thing called a complex number. I took a class in college called complex analysis, but we just learned how to do the math with, and we never learned like what it was really used for. So I was teaching math at my other school. I had this kid that had graduated. He was now an engineer at Boeing, right? The airplane place where they make airplanes and they make helicopters and stuff like that. I was telling him in church one day, I was like, Danny, I said, I'm teaching this imaginary number stuff, and I know how to do the math. I said, but do you guys do any stuff with imaginary numbers? And we talked for like an hour after church, And he was so excited to tell me about all the stuff that he does with imaginary numbers. And he's an electrician. He's an electrical engineer. He's not an electrician where he goes to houses and pulls wires and stuff. But he's an electrical engineer. And he said, I use this stuff all the time. And he was telling me all this stuff. He was like way over my head. I didn't understand half of what he was saying, but he was so excited to tell me about how he used imaginary numbers in his day-to-day job. So it can be used, all right? And it is practical. And they are numbers, they're just not real numbers, okay? It's a completely different number set, all right? And I took a whole class, and basically what we did, we kind of like did calculus with just imaginary numbers. That's basically what that class was. And so it's a different world out there sometimes. All right, when are we out of here? 15? Okay. Let's do this. We'll do this next whole section. We'll quit after this. This is pretty easy. This is called approximations. We already talked about approximating, right? The dot, 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 and all that kind of stuff, and the squiggle equal sign, approximately equal to. But this time we're going to do a little bit of rounding. I know you've done that kind of stuff before. But they're going to introduce a word that maybe you have not heard before. They call it truncating. You ever hear that? Truncate? Truncating? I'll write down truncating. All right. So truncating is when you just drop all the digits after the digit they tell you. All right. So, for instance, I'll give you an example. What if they say, what if you had this number, I'll put this number up here, 20.9. I could make up any numbers here, it doesn't matter. I'm just going to use the ones from my notes though. Okay? What if you had this? And they say, what if they ask you to approximate this number by truncating, right? This word truncating to 2 decimal places. So it's not your normal everyday rounding. Okay, all you're doing is after the second decimal place, you're just getting rid of everything. You're not going to see like which one's bigger than 5 or less than 5. All you do, if I say to truncate it to 2 decimal places, that means you stop at the second decimal and you get rid of everything else. So what would your approximation be? I'll put a little squiggly equals thing. It'd be 20 point what? 9 what? 8. Because truncating means you go to the second decimal and then you just get rid of everything afterwards. You don't look at the next number to see if it's bigger than 5 and all that kind of stuff. Okay, that's truncating. Everybody understand that? Yeah, it's pretty easy, isn't it? It's a word you probably have not heard before, is my guess. Is that true? You probably have not heard that word before. Now, the second one, you've definitely done before. You've heard it before, and that's just regular rounding. You know how to round numbers, don't you? So what if they said approximate this number by rounding to 2 decimal places? Instead of truncating to 2 decimal places, we're going to round it to 2 decimal places. So you're going to go put approximately 20.9, and then what do? We look at the second decimal place, and then you look where? To the right of it, and if that number to the right of it is what? 5 or bigger, then you take that number that we circled and you round it up. If it was 0, 1, 2, 3, 4 or less than 5, we would just keep that the same. So do we round this up or do we keep it the same? Come on, you're paying attention to the hallway. Right, you'd round it up, exactly, 9, 9. So that's what it would be. So we're approximating both of them, okay? But this is by truncating, this is by rounding. All right, and sometimes the truncated answer and the rounded answer are the same answer, all right, because sometimes you don't round it up. Does that make sense? So for instance, what if that 7 wasn't a 7 or a 5? What if that was a 2? Would you round that 8 up when you rounded? No. So the truncated answer and the rounded answer would be exactly the same. It just depends on what that number to the right of it is. So that's pretty easy, isn't it? All right, just know that word. Have you ever heard of truncated before, truncating? Probably not, all right? But that's basically what it is. They give you this big, long example. For example, 6, It's so many decimals. I just don't want to write everything out. I think you got the idea, okay, with this. So if you want to look in your book, right, has everybody gotten their book on their, anybody go home yesterday and put it on their computer? Okay, make sure you do that, okay? If not, you should have it on your phone. You got to have it on your phone by next week, okay? You definitely, because I'll be giving homework problems next week. Probably not today or tomorrow. Well, I know not today. I think that's a good spot to stop. We've got just a few minutes left and starting a completely new subject. So no homework, and we'll do a little bit more tomorrow.